All right, today we're pulling back the curtain on a coding technique that is, no joke, a secret weapon. It's something that interviewers absolutely love to see, and it's what makes real-world applications fast and efficient. It's simple, it's powerful, and it might just change how you approach problems. When it comes to writing great code, it often boils down to this one simple question. Are you going to take the long way around, looping through your data again and again, or are you going to find that clever, elegant solution that gets the job done in a single pass? That's the challenge we're diving into today. So let's really look at this. On one hand, you've got the brute force approach. You loop through once to count everything up. Then you loop through a second time to rearrange it all. And hey, it works. It gets you the right answer. But it's slow. On the other hand, you have the optimal approach. This is where you do everything at once in one beautiful single pass. And that efficiency is what separates good code from great code. And the technique that gets us there is the hero of our story, the two-pointer pattern. The idea is it's brilliant in its simplicity. Instead of having one little iterator chugging along through your data, you use two. You can have them start at opposite ends and race towards the middle, or have one go faster than the other. It's the perfect tool for problems with sorted arrays, finding pairs, or really any time you need to look at both ends of your data at the same time. To really get a feel for this, we've got to see it in action. So let's start with a nice, simple challenge to build up our intuition. We're going to sort an array that only has two different numbers, zeros and ones. Okay, so here's our mission. We've got this jumbled up array. The goal is simple. Push all the zeros to the left, all the ones to the right. And the rule is, we have to do it in just one pass. No cheating. And here are our tools for the job. We have pointer I starting at the very beginning and pointer J starting at the very end. Think of I as the bouncer for the zeros only section and J as the bouncer for the ones only section. They're going to work their way towards each other. So here's the game plan. Pointer I is going to move to the right, and as long as it sees zeros, everything's cool, they're already in the right spot. The same goes for pointer J on the right side with the ones. But the magic happens when pointer I bumps into a 1. That 1 doesn't belong there, so we swap it with whatever J is pointing at. The space between I and J is our unprocessed zone, and with every swap, it just gets smaller and smaller. And look at that! After just a few steps, you can already see these zones forming. We've got our clean section of zeros on the left, our clean section of ones on the right, and our two pointers I and J have gotten much closer. That messy middle part is shrinking fast. And boom, once I and J finally cross paths, the job is done. The whole array is sorted perfectly. And we did it all in one single efficient pass. No extra loops, no wasted time. That is the elegance of the two-pointer pattern right there. Okay, feeling good? We've mastered two colors, but now it's time to level up. We're going to tackle a classic computer science problem, sorting three colors, zeros, ones, and twos. It's famously known as the Dutch national flag problem because it ends up looking like the red, white, and blue stripes of the flag. Now, since we have a third value to deal with, our two-pointer setup needs a little bit of help. We're going to keep pointer I for our zero boundary on the left and pointer J for our two boundary on the right, but we're also bringing in a third pointer, K. Think of K as our main explorer, the one that's actually going to walk through the array and decide what to do. The whole dance really comes down to three simple rules for our main pointer, K. First, if K finds a 0, that 0 belongs at the beginning, so we swap it with I and move both I and K forward. Easy. Second, if K finds a 1, well, 1s belong in the middle, so it's in the right spot for now. We just leave it and move K along. Now here's the really clever part. If K finds a 2, that belongs at the very end, so we swap it with J and pull J one step in. But notice, we don't move K. Why? Because the number we just got from J's spot is a mystery. It could be a 0, a 1, or another 2. We can't just skip it, so K has to stay put and check it out on the next turn. So far, we've only been playing around in arrays. But the true test of a great pattern isn't just that it works on one thing, it's how versatile it is. So let's see how this exact same idea, using multiple pointers, can solve a totally different problem in a totally different world. Linked lists. So here's our new puzzle. We need to remove a node from this linked list. But the catch is, it's defined from the end. So in this case, we need to remove the second node from the end, which is that number 4. And what makes this tricky is that in a linked list, you can only move forward. There's no back button. You can't just jump to the end and count backwards. So how do you solve this? Well, the brute force way is to make 2 trips. On your first pass, you walk the entire list just to count how long it is. Then you do some math, figure out which node to delete from the beginning, and you walk the list a second time to go find it. It works, but you know where this is going, right? The two-pointer way does it all in one trip. Before we jump into the solution, let me introduce you to a little trick of the trade that makes life so much easier: the dummy node. It's just a placeholder we stick on the very front of the list. Its whole purpose is to clean up our code. Deleting the first node is always a tricky edge case. But if you have a dummy node, then every single element, including the original head, has a node before it. It just makes the logic simpler. For this problem, we'll use a famous variation called the fast and slow pointer technique. We start both a slow pointer and a fast pointer at our new dummy node. Then, the first thing we do is give the fast pointer a head start. We move it forward n steps. In our example, n is 2, so the fast pointer jumps 2 spots ahead. This creates a fixed constant gap between them. And here comes the payoff. Now that we have that gap, we move both pointers forward together, 1 step at a time. Slow moves 1, fast moves 1. We keep doing this until our fast pointer hits the absolute end of the list. And because of that initial gap we created, guess where our slow pointer is now? It is perfectly positioned right before the node we need to delete. All we have to do is reach over, bypass that target node, and the job is done. 1 pass. It's beautiful. So, what's the big takeaway from all of this? It's not about memorizing the solution to the Dutch national flag problem. It's not about memorizing how to delete a node from a list. It's about training your brain to see the underlying pattern. Once you really understand a pattern like 2 pointers, you'll start seeing places to use it everywhere.
And that's the question I really want to leave you with. Great coders don't have a giant library of memorized answers in their heads. They have a toolkit of powerful patterns. So the next time you get stuck on a problem, take a step back. Don't just search for the solution. Search for the pattern. Thanks for tuning in.